Hello, good morning, everybody. So today we are going to continue lecture on chapter 5, a new chapter. New chapter will be started with lecture 16. The topics covered will be number 1, Bode diagram, and number 2, the Bode plot for constant real zeros and poles. Okay. So this is a extract from the CI, course information. Basically, in chapter 5, these are the topics to be covered. We're going to learn about the type of filters and its application. We're going to see the characteristics of a frequency response. Okay, and then the filter circuit. Yeah, we're going to see how this filter circuit will looks like. And I will emphasize for this course will be only on a first order filter. Yeah, first order filter. So this will be described further in lecture 17 after this. Yeah. And for this lecture, basically the Bode diagram is a representation of a transfer function. Yeah. So this is the topic that will be learned in lecture 16. Yeah. Which is actually a representation of a transfer function. The rest of these topics will be covered in lecture 17 and lecture 18. Okay, so let's have a look at this diagram. This is a system, yeah, a system which is based on the Laplace transform, the S domain. So we have learned the S domain in chapter 4 before. Okay, so in this diagram, we have a system where AS is the input, HS is the system's response, yeah, system response, or what we call as a frequency response. Okay, and VS is the output of the system. Okay, so the ratio between the output and the input will be the HS, yeah. HS is the ratio between the output and the input, and this HS, as I mentioned just now, is a frequency response of the system. And also, we also call this as a transfer function. Yeah, transfer function of the system. So these are the same, same things. Yeah, frequency response and the transfer function. Okay, so let's put HS, for instance, to be 100. Multiply with S plus 1 over S plus 10, S plus 100. Okay, so this is a typical transfer function of the filter. So our task now is actually is to sketch, yeah, is to sketch what should be the pattern, yeah, what should be the HS looks like, yeah, what should be the HS looks like. Okay, so this is the use of the Bode diagram, yeah. So Bode diagram basically is a representation, yeah, is how you interpret, is how you represent the transfer function, the HS. Okay, so we're going to see how the HS can be displayed. Yeah, can be displayed in terms of its amplitude and in terms of its of its phase. Yeah, with regard to the frequencies. Yeah. Okay. Right. So by this slide, I hope that you understand what is the purpose of Bode diagram. So in short, Bode diagram is a tool which is used to represent the transfer function of a system. Yeah. Okay. All right. So let's proceed with the Bode diagram. Okay. One more thing is that Bode diagram will be learned further in a control subject. Yeah. So you're going to learn a Bode plot in the control subject later on. Yeah. Okay. So Bode plot is a graphical technique which can be used to display the frequency response or a transfer function of a circuit. And basically, a Bode diagram consists of two separate plots. Yeah. The first one is a variation of the magnitude with regard to the frequencies. And secondly is a variation of the phase angle with regard to the frequencies. Yeah? Okay, so normally Bode diagrams will be plotted on a semi-log graph paper. Okay, so this is similar graph paper. I'm going to show you this graph paper of this. Frequency is plotted on the horizontal log scale, yeah, while the amplitude and the phase angle are plotted on the linear vertical scale, yeah. Okay, so this is what we call as a semi-log graph paper. Okay, so the horizontal is your frequencies, okay, whereas the vertical is the amplitude or the phase angle, yeah, amplitude or the phase angle of the transfer function. Right. The frequencies is plotted in a logarithmic scale. Yeah, logarithmic scale. So you can see logarithmic scale on top of this. Yeah. So we have 1.5 to. So this is what we call as a logarithmic scale. Okay, and the scale is in a power of 10. Yeah, it's in a power of 10. So in this graph paper, I start the graph from 10 power negative 2, followed by 10 of negative 1, 10 power of 0, 10 power of 1, and 10 power of 2. So this is not fixed, yeah? So you can start either from 10 power of negative 3, or you can also start from 10 of power of negative 1, and so on. It depends on the frequencies value of your transfer function, yeah? And the vertical scale is linear. Yeah, you can see the vertical scale is linear. And this is the scale for the amplitude and also for the phase angle. Okay, right. So just to remind you that for our course, we are not going to use a logarithmic graph paper or semi-log graph paper because semi-log graph paper is used when there is a need to plot, yeah, or to draw the Bode diagram, to plot or to draw the Bode diagram of the transfer function. But if you are requested to sketch, yeah, to sketch the Bode diagram or the Bode plot, yeah, sketching does not require the use of semi-log graph paper. Yeah, so sketching we just need to know the pattern. Yeah, you just need to know the pattern of the Bode diagram. Yeah, so you don't have to use the semi-log graph paper in this course. Yeah, so please bear in mind this. Okay. Uh, uh, so the transfer function basically involve the multiplication and division of factors associated with the poles and zeros of the HS. Okay, so I believe that this is what we have seen in the first slide of this. Yeah, this is the one. So the HS normally involve the multiplication and division, yeah, of the pole and zero. So I believe that you have learned. I have mentioned about the pole and zeros to you in chapter 4 before. Yeah. So the pole is the root of the polynomial. Yeah, the denominator. Yeah, the denominator part. Whereas the zeros is the root of nomial for the nominator. Yeah, nominator and denominator. So zeros is the nominator part. Pole is at the denominator part. Yeah. Okay. So HS basically involve the multiplication and division of factors. So we know that these operations, we have the multiplication and divisions. So these can be reduced to just addition and subtraction, or just simply algebraic operation. Yeah, by expressing the amplitude of the HS in terms of logarithmic value or decibel. Yeah, yeah. So we can write the S or Hg omega. So it's similar things. Yeah, HS and Hg omega is a similar things. Yeah. So sometimes I'm using HS, sometimes I'm using Hg omega. So both are similar. Yeah. So the HS can be written in dB to be 20 log of HS or 20 log of Hg omega. So by this you can write the amplitude in terms of simply the addition and subtraction. Okay. Okay. So HS can be categorized as a constant. It can be categorized as zeros. or poles, yeah, which will be used in determining the shape of the Bode plot. Yeah, shape of the Bode plot. Okay, so three things or three important characteristics need to be understood now. HS can be in terms of a constant. It can be in terms of zeros, or it can be in terms of the poles. Yeah. Okay. We're going to start with a shape of the Bode plot when we consider the Bode plot is just having constant terms. Yeah. Okay. So let's put the HS to be equals to K, where K is a constant. Yeah. HS equals to K is a constant. So from this, we can write that the amplitude for the HS or the amplitude for the Hg omega is simply 20 log of K. Yeah. So 20 log of K will give us a constant value. So that is why when we consider the amplitude plot, okay, so this is your amplitude plot, the amplitude in dB versus the frequency in omega, we are going to have a constant value of the amplitude, which is 20 log K. Whereas for the phase angle, yeah, since we have only K, which is a constant, so the phase angle will only be 0, yeah. So that's why for the angle, it will be 0 degrees. Yeah, so this is a line of your phase angle plot. Okay, so why we have 0? Because consider that HS is a complex number, A plus JB. Yeah, A plus JB, for instance. So if B is 0, you don't have any imaginary value. So the phase angle or the angle will be 0, yeah, because we know that the angle is the arctangent of imaginary value divided by the real value. So since the imaginary is 0, so the angle will be 0, yeah, because arctangent of 0 will be 0. Okay. Right. Next is when we consider that the Bode plot for the HS, where HS is only having a pole at origin terms. Yeah. So what is meant by pole at origin? So the pole at origin is where we have the HS equals to 1 over S. Yeah. Where the pole or the root of this pole is 0. Yeah. All right. So we have HS equals to 1 over S, or Hj omega equals to 1 over J omega. So we know that in the amplitude in dB for this Hg omega will be a negative or 20 log of omega, because when we write this in terms of the amplitude in dB, we are going to have 20 log 1 minus 20 log of J omega. Yeah? So 20 log 1 will be 0. So that's why we have the amplitude to be negative of 20 log of omega. Okay, and you can prove on your own that the phase angle will be negative of arctangent omega divided by 0, which will give us negative 90 degrees. Okay, so for this, the Bode plot for the pole at origin, yeah, in terms of the amplitude will be a straight line, yeah, a straight line with a slope of negative 20 dB per decade, and the plot will pass through the value of omega equals to 1. Yeah, omega equals to 1. Because when you substitute omega equals to 1 in this equation, yeah, when we substitute omega equals to 1 in this equation, the amplitude will be equals to 0. Okay, that's why the graph for the pole at origin will be a straight line which pass through the value of omega equals to 1, and the slope of this graph will be negative 20 dB per decade. So what is decade? So maybe I forgot to inform you about decade just now. Okay, back to this semi-log graph paper. This is 1 decade, yeah, which means that from 10 power of negative 2 to 10 power of negative 1, this is 1 decade. 10 power of negative 1 to 10 power of 0 is 1 decade. And likewise, from 10 power of 0 to 10 power of 1, this is 1 decade. Okay, so this is what we call as 1 decade. So in this graph, we have 1 decade, 2 decade, 3 decade, 4 decade, and 5 decade. Yeah. Okay, so back to this graph just now. So if you imagine that this is 1, so if this horizontal axis start at 10 power of negative 1, yeah, 10 power of negative 1 or 0.1 value. So this graph, the starting point for this graph, yeah, at a vertical scale will be at positive 20 dB. Yeah, such that the graph will be having a slope of negative 20 dB per decade. Yeah. Okay. All right. Whereas for the phase plot here, the phase plot, knowing that the phase angle is constant at negative 90, that is why the phase plot for the pole at origin will be a constant at negative 90 degrees. Okay. Yeah. All right. So let us proceed with the third condition or third situation where we have the transfer function is only consists of zeros at origin. So zeros at origin is where the HS is equals to S. Yeah, HS equals to S is considered to be a case of zeros at origin. Okay, so if we write the HS to be Hj omega, so we are going to get Hj omega equals to J omega. And we can write the Hj omega in terms of a dB scale to be 20 log of omega. Okay, and based on this, we can write that the phase angle will be equals to arctangent of omega divided by 0. Yeah. Why 0? Because we know that the phase angle is arctangent of imaginary value divided by the real value. So from these terms, we know that imaginary value is omega and the real value is 0. So that is why we have the arctangent is omega divided by 0. So this will give you infinite, and the arctangent of positive infinite will give us positive 90 degrees. Okay, so from this amplitude and the phase angle value, we can then sketch the amplitude to be look like this. Yeah. Okay, this is as if we compare with the pole at origin amplitude plot, it is a bit different. Yeah, because remember, if we get back to this point origin, it is a negative 20 log of omega. So that's why we have this as the amplitude plot. Whereas for the zeros at origin, so we have 20, positive 20 log of omega. So the plot is having a positive slope, yeah? But still, the graph or the slope will pass through or will be having a value of 0 at omega equals to 1. Yeah, because we know that from this equation, when omega equals to 1, the value of this amplitude will be 0. Okay. So the slope for this will be 20 dB per decade positive. Okay. So as before, if we consider the starting point for this horizontal scale to be at 0.1, so 0.1 to 1 will be 1 decade. Yeah, 0.1 to 1 will be 1 decade. Yeah. So we can say that at this particular position at the vertical scale, the value of this intersection will be at negative 20 dB. Yeah, because this is 1 decade. So this point here should be negative 20 dB such that the slope is 20 dB per decade. And for the phase plot, since you have a positive 90 as the phase angle, so the phase value will be a constant of 90 degrees. Okay. All right. So we have done with 3 conditions or 3 types of the Bode diagram. The first one is for constant. Second one is for the pole at origin. And the third one is for 0 at origin. So after this, we are going to proceed with the real poles and real zeros plot. Okay, so I'm going to stop here. I'm going to continue on the second part of lecture 16. Okay, so thank you very much. See you after this.